Hello and welcome to class 5 of Particle Fundamentals and Fuzzy Logic. So in this class, we're going to take a look at the tilt axis, which will keep the shark fin up in the air, which is what sharks like to do, and also take a look at some banking behavior. So here we can see the tilt axis is getting out of hand a little bit because as our target direction is rotated, it's rotating about the up, and because the up is always getting realigned to the target, it's distorting naturally. But more so than that is we might want to have a constant state of adaptation if we were to do some creative things with the up vector, like have it swashing around with some environmental effects like we'll do in latter classes, or also have some banking behavior, meaning that the shark turns into the direction so that it can turn quicker. Okay, so let's take a look at that first. And this should, at this point, be a review of the first parts of the rotational stuff we've already gone over. Okay, so diving in here. Okay, so let's call this previous up and down rotation, shark, up, down. Okay, and now let's finally add some tilt. Okay, so let's call this shark, tilt. And diving in. So what do we need for the tilt? Well, we definitely need the direction and the up. So let's start by importing those things. Shark direction. Shark up. For this, we're going to need a feedback so that we can actually adjust the up. What we're essentially doing is abstracting, or as I often say, taking a step back from directly coding this shark up vector. So for that, we need a target. We need somewhere for this shark up to seek, because, I mean, how does it know it's supposed to go up in y, 0, 1, 0? So let's give this a new piece of data. Let's similar to the shark direction, we had target vac. So similar to that, let's do shark target up. There we go, and that'll also be a vector. And this time, let's, in case it doesn't exist, let's say export always and set the default to 1. So if that worked, we should have this guy present here. Okay, so the idea is that the shark up is always going to be seeking the shark target up. And let's view the shark target up. Okay, so it's a dark green. All right. So wherever our light green guy goes, there's a dark green here it should be trying to get to. All right, so now let's just apply a few of the same concepts. So for the light green up vector to get to the target up vector, we need to give this an axis to rotate on. So for that, we need to do what we've done before and align one vector and flatten that along the axis of another. So we're going to use the flatten on axis. And let's just visualize that with a test vector. So, okay, so the axis is going to be shark direction, and this is the vector we want to align. So let's see what that ends up looking like. And you see, so now it's going, the green one is going to go to that red one instead of cutting over axes and kind of going in an angle. It's going to be rotating on the axis it should be rotating on, which is this guy. Okay, so and that's also a more accurate angle measurement of where he wants to get to. Okay, so now we have to rotate the green one progressively to the red one, and let's use our asset we've made in the previous class, the live fuzzy rotate degrees. Okay, so the axis we're the vector we're rotating is the shark up. We want to rotate it to the target, which is that. We want the spin axis to be the shark direction. With these parameters, it's important to have unique names if we're going to be especially controlling lots of sharks in mass. So just be wary of using an asset and the same names. Otherwise, if you adjust something at SOPs level, it would adjust everything that has that name, as we'll do in later classes. So here I'm going to call this max degrees tilt. There we go. And then for the strength, tilt strength. That's the strength of the turn. Let's plug that in. Let's put on some values. So the detect, let's try that 45 degrees for the strength. Let's set it really mild for now. Correction of 30 degrees a second. Okay, and now we actually need to rotate it. So rotate vector by degrees. There's our degrees. Our vector we want to rotate is the shark up. The axis we're rotating on is the shark direction. And then let's complete the feedback loop. Use this node. Go. And see what happens now. So it should be continually realigning itself to be even with the circle now. And there he goes, really slow, but you can see it happening. Let's speed that up a little, maybe 90. Yeah, so he's not having the same kind of issues that we saw previously. And now let's get into some banking, because there's a lot of visual interest we can add by having the shark turn into the direction that it's about to swim in. So for that, let's use a different visualizer. Let's use our target. There we go. Okay, so now let's just see how this is doing. And we really shouldn't have much need to adjust the up in its current state because it's completely flat. But now let's add in some banking behavior. So the idea is that as this target turns, as it readjusts, as the shark turns in this direction, the fin should go this way. So the shark can turn into the direction. As soon as it gets there, it should use our adjustment system and realign itself. All right, so how are we going to do that? Well, first we need to know how much it's actually turning. So we don't actually have that information in the shark tilt. We could certainly gather it, but it'd be really hard. And we already have that information present in our left and right direction down here. One thing first, let's make this curve a bit more organic. There we go. Okay, so the left and right direction already has access to that. All right, so we need to adjust our live fuzzy rotate degrees digital asset a little bit. Okay, so because that's all happening in here, it's already knowing which direction it turns, and it's already knowing how strong it's going to turn in that direction. So allow editing of contents. I'm going to go in and let's actually name these things a bit too. So I'm going to use a null. Let's call this degrees. That makes more sense. And we want to know the strength of the turn. So we could use the result of our curve. The problem there is, what if it's an extreme curve? And it's kind of locking that decision into everything we're going to use based on this. We might want to do banking curve very differently than a rotate and acceleration curve. So here I'm going to use the result of the ramp here to determine how much to bank. So this will be our turn strength. You can use it for lots of things. You don't have to just use it for banking. Maybe there's other conditions. Okay, And then finally, we need to know which direction it's turning. So for that, we want this guy, the positive or negative. Okay, let's put that in there. There we go. So we have degrees, strength, and turn sign. All right, so let's save this digital asset. And that shouldn't have affected our other systems. Should still be working fine. But we now want to use these values, and let's export those. So we need both of these in order to produce the banking effect. So we'll call this shark turn strength. Make sure that name isn't already taken. There we go. Got that. Shark turn sign. And this is where things get really interesting for me, because once we have a semi-simplistic and yet working system, then we can elaborate on it, and we can use a piece of data from one node and feed that back into a system for another node and form really great fuzzy logic dependencies. Okay, so let's make a little color preview. I'm going to say if it moves left, I'm going to turn the color blue. If it turns right, I'm going to turn the color green. Okay, so let's see. So we need to fit the sign to the 0 to 1 range, and we'll do a color mix. Let's do blue and blue for left, and green for right. Okay. And then let's color mix that by the turn strength. So if the turn strength is high, it'll show up as colored, and if it's low, it would turn up as desaturated white. Okay, so here we go. Let's try that out on the color. See if it goes. Okay. So what's it going to do now? Okay, so it's going in the wrong direction for my sign, so I'm just going to negate that. There we are. So left is blue, and so now it's easier to keep track of that the attributes are actually functioning properly as they go into another node. Okay, let's call this color preview. There we are. Okay, now let's use these two pieces of data to produce the banking effect. Okay, so now going back out, we're going to go into our shark tilt, where we've just been working. Okay, so what are we going to bank? Well, we actually want to bank where the shark considers up, not the current up vector, because we're just going to be a constant fighting state with our existing system if we adjust the current up vector. So the vector we actually want to manipulate is going to be the target up. So let's make a subnetwork, and we can just call this bank. There we go. Okay, so the target itself is what's going to be banked according to the left, right. All right, so let's import those attributes. Let's import shark turn strength and shark turn sign. Okay. And so now, if the shark turn strength, and these should be floats. Okay. If the shark turn strength is high, then we want to bank it more. So let's fit this. Actually, we can just multiply it because it's already 0 to 1 value. And we could also put a ramp on here. Let's call this banking ramp. Okay, so in comes the turn strength. We remap it. Now we're going to multiply this by the maximum amount of banking degrees. Okay. So there's that. And then finally, we'd want to multiply that by the sign to go to rotate positive or negative. Now this will be an absolute hard-coded thing, but that's okay. It's not going to be jumpy or anything because first of all, there is a gradual rotation of the direction, and also the up vector has graduality to it as well. So it's going to slowly adapt, so it's okay to change this guy around. Okay, so there's our going to be our degrees we should rotate. What are we going to rotate this about? Well, we're going to rotate this about the shark direction, which is the thing that's banking. So let's put the shark direction in here. And we'll do our rotation again. Okay, so this is the degrees we want to rotate. The vector we want to rotate is the target up vector. And the axis will be the shark direction. Let's see how this works out. Let's try really extreme banking so that we can see it. Okay, so it's banking in the wrong direction. All right, so I just need to negate the sign. Let's try it again. Cool. Okay. And now that we know it's working, let's ease off on that banking a bit. And let's make the up adjustment a bit more responsive. Let's also give this curve a bit more organic feel as well. And now that we have all these rotational systems working together, it'd be nice if they played together a bit more smoothly. We don't want jitter going on. We don't want it to always be struggling to adapt. So we discussed in a previous class about adaptation, meaning taking a step back and using an attribute to adapt to a target value. You can do it with a vector like we just did with the banking, or we can do it with a simple float. And in this case, I think we might want to do it with a float to change the adaptation degrees for a number of things, particularly the adaptation of the upwards vector, and maybe of the directional vector, the shark direction, rotate degrees as well. Okay, so let's really dive a little deeper and see what's going on there. All right, so and anytime I really want to visualize what's going on, I would probably want to see it in a graph, and chops is a great way to do that. So let's call this test adapt. And let's just make a constant that we can test on a constant data channel. A data channel would work the same way as a floating point number, and this way we can see it quite nicely. Here's our motion view. Okay, so with this channel, let's make this channel about 100 seconds. Okay, have our channel here. And let's just give it random sets of values from 0 to 1. So I'm going to use an expression chop, and let's say random of the current index $i plus a seed offset. Okay, so we get that. And then we're just going to compare that is less than a percentage. And now we only have 5% triggers. Let's make it actually a lot less than that. Only a few. Okay, so we're going to see what it's doing, how it's adapting to these. And let's multiply this conditional statement with another random to give them random values. Let's make a different seed on there. It should be multiplying. Okay. So, all right, so we got a random set of triggers, and now let's hold this value. And now we have a random set of values that our test float would try to achieve. Okay. Call this target value. All right, and I'm just going to make a SOPs network. Let's make a pop network. Let's give it a single point. And only birth on the first frame. Okay. And we can use this for our test. And then I'm just going to, let's just call this something generic that we're going to test. Let's just call it value. That's about as generic as we can get. Okay. And just to test to see if it's reading in, let's just give it an arbitrary value for now. Okay. And now with our geometry chop, we can read from test pop, popnet, and we want to be reading value. Okay, so that's 0.3. Cool. And we want it to be animated. And maybe not the full 2000 frames I have here. Let's just test out with frame 500. So I'm going to use frames, start and end 1 to 500. There we go. Let's test on this for a few minutes. Okay, so I want to get the target value into the popnet. So instead of 0.3, let's call this target value. And with this, we're going to give this the chop expression to read that from our random triggers. So let's see, so that would be a relative reference up a few levels. So there's our target value, and we just need the channel name, which is chan1. Let's try that out. Okay, so we're reading in this data as a parameter into our pop. And now let's do that adaptation, and let's give it a little bit smoother character. Okay, so anytime we want to abstract a value, then we'd have to be importing it and exporting it. So here's our value going out, use this node, and we want the value going back in. So here's this. Here's where we cause the feedback loop, and instead we're going to be adding an increment. Okay. So we'll call this maybe add increment. Need to multiply this by the time increment, as well as the sign if this value should be rising or falling. So we get that from subtracting the value and the target value. Okay, we've done this before. So this is just the initial setup. So adding increment, let's do like 0.1, let's say. Okay, and once again, I have the wrong direction on my subtract. I always do that. Also, we don't want to be multiplying directly by the target value minus the value. We want to be getting the sign just to make it go up or down. Not a specific amount yet, because what if we weren't working in a 0 to 1 range? Okay, so here it's adapting and we get these kind of jitters that we had before, and really we want to smooth these out. Okay, so for that, we're going to do some mixes. So this whole thing is where we're adding the increment to the value. So let's encapsulate that and then work on some ways to smooth this out a little bit, smooth this progression out a little bit. Okay, so all this that can be add inc to value. Okay. And now what would happen if we were to mix a certain percentage? Well, we need to know the percentage in the first place. Mix the percentage of the target value. And that would create a really smooth transition, but it would never actually get there. Okay, so how do we know what percentage we are from our current value to this value? And we can get that by subtracting the target value from the value. So this is the difference. And we'll do an absolute. So we'll call this maximum difference. Or actually, it's really just the difference, so difference. Okay, to get the maximum difference, we'd need to know how far up and down these values are going to go. So let's do a minimum and a maximum target value. So min target value, and we happen to know that's 0 on this graph. And let's do a maximum target value. Have that default to 1. And in this case, it is 1 that it could possibly be minimum maximum. Okay, so now let's fit the difference from the minimum difference possible and the maximum difference possible to 0 to 1. And now let's just blend based on that. So the closer it's going to get, the more it's just going to blend to the target value. If it's far away, it'll increment. Okay. And this is backwards because 1 would be, if it's far away, we actually want it to be going into adding increments. So let's switch these. Okay. And so now it's really adapting pretty strongly, isn't it? And what if we want this to be a bit more gradual? So let's just use another mix, and then we can mix between the incoming value and the target value to get more of a blending effect as we get closer and closer to the target. So here, let's add in a mix. Going to be mixing in the target value from the value, the current value. Let's try 0.1. So this should give us much more gradual progression. Okay, and let's have this as a parameter that we can manipulate. So let's call that blend target. So here's a faster adaptation rate. And so now we're getting some nice smoothness. It's not adapting instantly to that value. So we could use a system like this on any particle attribute that we chose. So I've gone ahead and made this a digital asset. Here's a float. So with all those same parameters. So let's see, mix percentage, depth increment, target maximum would be 1, target minimum would be 0, target value would be our chasing our value here. There's our target value. Okay. Now, if we wanted something even more smooth, that's really where we have to have this value adapt, and then you'd get more of a second order or an acceleration to use if you really needed that smoothness. Since most of our vectors that we're using already have an adaptation associated with them, in the fact that they're adjusting gradually, then we already have second order smoothness, but let's say you didn't. So let's see what happens when we adapt the target value. All right, so I'm just going to use another one of those. We need a parameter for a feedback, so maybe adapt target. And use this node. Okay, so that's going to be going out. We're going to be reading the same thing in. Okay, so here's our adaptive value. This is our target value, same target. Minimum and maximum, adapt increment, okay. And a bit of mixing on that as well. Okay, so now instead of using this target value, if we wanted some smoothness on this side as well, then the target will adapt, and we'll use the adapting target to chase it with a value. Here's our target value. There we go. And we should set the maximum as well here. Otherwise it won't be blending. Okay, so now we can see that it's got some smoothness on this side, and generally we have a lag at the particle level. Okay, so let's see what happens. And this is, hope you enjoyed testing this out on a graph, and we can really understand things at play here. So it takes these set of values, and it's really trying to gradually adapt to where that can go, and that'll create a much more organic simulation, because anything that's alive won't have an instant response time. It's going to take a while, and the more of its objective it completes, it's going to be a little less aggressive in getting there. So classic ease in and ease out. All right, so let's apply this adaptation to the direction. Okay, so maybe the shark left and right direction. Okay, so we want to adapt the degrees. And so let's pay attention to how it looks right now. It looks cool, but it doesn't really look like it's underwater. Everything is kind of in motion underwater. And it very precisely realigns itself. Okay, it's better than not working at all, but now let's add a little bit of adaptivity. So in comes what we want to adapt, which is our degrees. Okay, so let's call this shark adapt dig. When input is connected, use this node. Okay, so this is what we're going to adapt. Our target will be our degrees. Minimum and maximum degrees, well, we really can get our maximum degrees from the detect degrees, because that's really the maximum it's going to be away from its curve. Adapt increment, let's try 10, and mix percentage. And now using our newly created parameter, we can use this for the degrees. And let's see what happens here. All right. So now we have the magic of particle attributes working together with feedback. So we've got all of our rotations working together, and then when it adapts, it's adapting, and it's always going to be a lot more organic, because it's never going to be a complete adaptation. It's always going to be getting closer and closer and never quite getting there. And the various strengths of each of our systems are going to be compensating in their own ways, and it gives a much more lifelike appearance, as well as the correct result that we were after, because that's also really important, as we don't want it to swim in a random direction that we don't want it to, but we still want a little bit of give. Hopefully we've learned a lot about rotations, and in the next lesson we're going to take a look at some rig integration and get this guy swimming around once again with all of our new rotational tricks.